Greetings. So, we will continue our discussion on second quantization, and today we will introduce the creation, destruction and the number operators. The destruction operator also often referred to as the annihilation operator, and basically our many particle system will be described in terms of single particle quantum numbers. These are elementary identical particles. So, they are indistinguishable, they are elementary, but we will continue to treat them as elementary particles even in the presence of correlations and even reconciling with indistinguishability, because you may not be able to number them or identify them by some names or numbers or colors, but they do have their intrinsic properties which are fundamental to an elementary particle. So, if you have an n particle system, then even in the presence of correlations we can talk about a certain number like n1 number of particles in state alpha 1. Now, what is alpha 1? Alpha 1 is a set of quantum numbers which describe a particular single particle quantum state. Okay. So, there is a single particle quantum state. It is not just one quantum number, it can be a set of quantum numbers, and these quantum numbers come from eigenvalues of those operators which commute with each other corresponding to whatever measurements are compatible with each other. So, you will have n1 number of particles in the state alpha 1, n2 particles in state alpha 2 and so on. So, this will be our description of the n particle system, and this is the way you would describe the system of indistinguishable elementary particles, whether they are fermions or bosons, but then of course the statistics is different. So, these are obtained as eigenvalues of a complete set of commuting Hermitian operators. These are number operators. So, this number n1 is an eigenvalue of a number operator which is capital N1. Okay. n2 is an eigenvalue of uppercase N2 which is a Hermitian operator. This is the number operator. These are called as occupation number operators, and this description is common to both the fermions and the bosons. Now, let us develop the Schrodinger equation, and up to a certain point we will carry the formalism forward. Yes, Suman. The number of particles. Okay, their eigenvalues give the number of particles in a particular single particle quantum state. Okay. So, you have for both fermions as well as bosons, let us say you have got a space spin space represented by xk, and a typical Hamiltonian for the many particle system is the sum of all the kinetic energy operators and certain two particle interactions. This is a typical Hamiltonian. Okay. The details will differ, sometimes we will have more complex terms, but notwithstanding the details, by and large a many particle system will be described by a Hamiltonian of this kind, in which the kinetic energy operators will sum over all the number of particles going from 1 to the total number of particles, and the two particle interactions represented by this V. In the case of fermions it could be the 1 over Rij, but in general it could be some two particle interaction. Now, the Schrodinger equation for this system would be a function of these n coordinates. Each of these x1, x2 up to xn is actually a set of 4 coordinates. So, there are 4 n coordinates, right, 3 space coordinates and 1 spin coordinate for each particle. They are collectively written as x1. So, there are these n coordinates and there is also a time dependence. So, this is the Schrodinger equation, and you need to solve this subject to whatever boundary conditions are appropriate for the physical situation under consideration. Now, this wave function will be represented in a basis of single particle states. So, these psi, so there are two kinds of psi which I have used. One is this psi, which if we may call this as an uppercase psi, and this is another psi which I may call as a lowercase psi. Okay, both are psis, but this is the n particle wave function. This is uppercase psi. This is a function of all of these n coordinates as well as time, and then you have these lowercase psi functions which are a function of single particle coordinates xk. So, this probability amplitude is a measure of the probability amplitude that a particle at coordinate xk will be in the quantum state Ek, where Ek is a set of appropriate number of single particle quantum numbers. It is not just the energy, it will have all other measurements which are compatible with the measurement of energy. Okay. So, it could include the angular momentum, it could include spin, and any other measurement which is compatible with the measurement of energy. So, Ek is a collective label, and this for one electron atoms, for example, this is a set of 4 quantum numbers n, l, j and mj, or it can also be n, l, ml and ms, but in the case of spin orbit interaction, j and mj are better quantum numbers and not ml and ms, but you can always carry out transformations from one to the other using the Clebsch-Gordon coefficients. So, essentially Ek stands for a set of appropriate number of quantum numbers which describe the single particle states, and these come from eigenvalues of a complete set of commuting operators corresponding to compatible observations. So, this is your Schrodinger equation, and you can write it as a product of single particle functions. Look at the coefficient will of course depend on these quantum numbers as well as the time, but then a general n particle state which is being written on the left hand side will be a linear superposition of all of these possibilities, inclusive of a summation over E1 prime, E2 prime up to En prime. So, there may be infinite possibilities in this set, okay, and all of these collectively represent the n particle system. Now, this is the most general description of an n particle state, be it a system of fermions or bosons. This part is common to both. So, you can write all of these multiple sigma notations as a single sigma notation, but the summation is over E1 prime, E2 prime all the way up to En prime. So, you must sum over all of them. These are time independent, the single particle states are independent of time. Okay. All the time dependence is in this coefficient C, this is where the time dependence is. Okay. So, there is of course a time dependence. The Schrodinger equation, the Schrodinger wave function is of course a time dependent function, as you can see from here, but the time dependence is not in these single particle states, it is in this coefficient C. This is where the entire time dependence is, in this T. Okay. So, the coefficients C are time dependent, the single particle states are not. You can always develop a formalism in which you can make the single particle states also time dependent, but that is a matter of detail, and those are special techniques which are devised to deal with the many body problem. I will mention some of them as the course develops further, but at this point we consider time independent one particle functions, one particle states, and the time dependence completely absorbed in the coefficient C. So, now we know that if you interchange the ith and the jth particle, if there is an interchange between I and j particle, then the wave function would either remain invariant, it will remain the same as before, or one interchange will lead to a change of sign of the wave function, and that depends on whether you are dealing with fermions or bosons, right. So, this is where the statistics comes in. So, all the statistics is contained in the properties of the wave function. Now, this is just a product of single particle states, and you are summing over all of them. Okay. So, the statistics is not contained here, the statistics is contained in the coefficient C. Okay. So, there is a one-to-one correspondence between the property that the wave function remains either invariant on interchange of particles for bosons or changes sign for fermions, and the properties of the coefficient C if you interchange two of these labels. Okay. So, this is the necessary and sufficient condition that the expansion coefficients C themselves must be either symmetric or antisymmetric. They are symmetric in the case of bosons and they are antisymmetric in the case of fermions. The expansion coefficient C is where the symmetry is now sitting. Okay. And this is a necessary and sufficient condition. You can prove this as a very simple exercise. I have already given hints about where the proof comes from, but essentially you notice that the statistics is now contained in the symmetry properties of the coefficient, that under the interchange of these quantum states Ej and Ei, if you interchange these quantum states, okay, the coefficient C will either remain invariant or remain the same amplitude, same modulus, but change its sign, okay, depending on your working with either Bose type of particles or Fermi particles. So, this is what we have got, and now the summation is over dummy indices, dummy variables. The dummy variables are our primed variables E1 prime, E2 prime up to En prime. So, they are going to be summed over. So, what we are going to do is to multiply the Schrodinger equation by this product of single particle states, but you take the adjoint. Okay. So, you multiply by the adjoint of these single particle states, by the product of these single particle states, and for a particular set E1, E2, these are without primes. Okay. The primed variables appear in this summation. So, they are dummy labels, we do not want to use them, since we are multiplying it by a particular set E1, E2 up to En. So, you multiply the Schrodinger equation by this set. Now, this is the result of the left hand side. You take the product of these single particle states with their adjoints and multiply the left hand side IH cross del psi by del t by this, and on the right hand side you have got the same factor pre multiplying H psi. Okay. Now, the next thing you do is integrate over all the coordinates. So, now your integration over x1 is actually not a single integration, but it is integration over 3 space coordinates and a summation over the discrete spin coordinate. Okay. So, each integration corresponds to 4, 1 discrete sum and 3 integrations over the space variables. So, you integrate over all the coordinates. So, this is IH cross is coming from here, it is also over here, and you integrate over dx1, dx2 up to xn. This is the integrand which is on the left hand side, which is this product of single particle states taken with their adjoints and multiplying del psi by del t, IH cross having written on the extreme left as a constant multiplier. So, that is your left hand side. On the right hand side you have got again an integration over all the coordinates x1 through xn, and what are you integrating is this product of single particle states with their adjoints pre multiplying H psi. Okay. Yes.
dx1 and dx2, those integrals are separated. So, x1, x2 are independent
Of course, x1 is a particular coordinate. Okay. Certain interactions might couple a particle at x1 with a particle at x2, right. So, there can be an interaction V which depends on x1 and x2, and that goes into the Hamiltonian. Okay. So, that is sitting in this Hamiltonian here. Okay. So, this is the expression that we have got, and the wave function we already agreed that a general correlated wave function, a wave function of a correlated system of particles, is written as product of these n single particle states weighted by the coefficients which contain the statistics. Okay. So, this is your left hand side. Track the time derivative which is on the left hand side, which is this partial derivative with respect to time, it is written over here, and on the right hand side you have got the Hamiltonian which contains the kinetic energy operators and the potential energy operators which may depend on the coordinates of two particles. Okay. So, this is your expression that you get on carrying out this integration. So, let us write it to the top of this next slide here, and now we are aware that these single particle states are essentially orthonormal. Okay. So, we work in a basis of orthonormal single particle states, and we exploit the orthonormal condition. So, this integral will be given by a Dirac delta in the case of continuum functions, or Kronecker deltas in the case of discrete functions. So, in general it is a delta function, and whether this is a Kronecker delta or a Dirac delta can be plugged in according to the context. In general we will simply use it as a Kronecker delta, but in general it could include the continuum states as well. Okay. So, you have got this orthonormal condition, orthogonality condition, and we exploit this orthogonality because when you are having this integration, okay, this coefficient C can be factored outside the integration, because this does not depend on the coordinates x1, x2, x etc. And then you have got the integrals of this kind, and wherever you have orthogonality you can get this delta function, and then when you sum over these E1 prime, E2 prime, En prime. So, if you were to consider this term, the only term that would survive is the one corresponding to E1 prime equal to E1, or like that, right, whichever is being considered there. So, you can exploit the orthogonality condition, and what you have on the left hand side is, after contracting these integrals exploiting the Kronecker deltas and the orthogonality of the wave functions, you get IH cross, then you have the time derivative of the time dependent coefficient C which contains the statistics. So, now you have got the IH cross del C by del T on the left hand side after exploiting the orthogonality on the left hand side. There is only one term that will survive under all of those integrations, right. That will be the coefficient C corresponding to a particular set which is E1, E2, E3, which is the unprimed set that we used in the previous step, right. So, that is the only term that will survive on the left side. On the right side I have written the term just the way it was without any further modification. So, you have got integration over all of these n coordinates, or 4 n coordinates if you like, and then you have got this adjoint product of single particle states, then you have the Hamiltonian here, and then you have got the complete wave function inclusive of the time dependent coefficient which has got the statistics built into it. Okay. So, this is what we have got, and we will now look at the right hand side carefully. On the right hand side you have got the Hamiltonian, okay, and the Hamiltonian for a many particle system is the sum of all these kinetic energy operators and a two center interaction. This is a general form of a typical Hamiltonian. So, you substitute this Hamiltonian by its explicit form consisting of the kinetic energy operators and the potential energy operators, which is coming from interaction between every two pairs of particles. Okay. So, this is your general form of the many particle Hamiltonian. Now, this is what we are getting from the Schrodinger equation for the n particle correlated system. Okay. So, we have now built in all the correlations. The statistical correlations are there, which are sitting in the coefficient C, and any correlations over and above the statistical correlations like the Coulomb correlations are also sitting in the fact that you have got a infinite set of these products of single particle states which have gone into your total wave function. So, all of them have been covered. So, now this is IH cross del C by del T on the left hand side, and on the right hand side you have got two terms, one coming from the kinetic energy term and the other coming from the potential energy term. So, it is the same two terms, but I have written them as the first term corresponding to the kinetic energy term and a second term corresponding to the potential energy term. So, I have only separated them because that makes it easy to handle them, because you already have so many terms and you do not want to mess with too much everything at the same time. So, this is what you have got. Now, let us look at the kinetic energy term, the first term, and you are carrying out integration over x1, x2, xn, etc., and all of these integrations can be carried out independently of each other. The kinetic energy operator depends only on one coordinate at a time, right. So, all of these integrations can be carried out on each coordinate separately. Okay. We will deal with the potential energy term a little later. So, first let us take the kinetic energy terms, and the kinetic energy term, the one which depends on the argument k, will have the operator T x k sandwiched between psi dagger and psi with the arguments x k over here as well as over here, and you have an integration over x k. Okay. All the other integrals will not have any operator, and you will simply have the orthogonality integrals psi even psi, this is integration over x1 psi e2 x1 dagger psi even prime x1, and you will have orthogonality integral between even and even prime coming from here, and then when you sum over even prime you can exploit the Kronecker deltas. Okay. So, that is going to make all these very many terms that you are dealing with, you will be left with very few because of the orthogonality condition. Again we will carry forward our discussion on the potential energy term to a later part and continue our focus on the single particle kinetic energy terms for the time being. So, you have got the single particle matrix element of the kinetic energy operator here and the orthogonality integral over here as well as here and so on, okay, right, all the way over x1 to xn. So, there are n integrals. Out of these n integrals, n minus 1 integrals will be the orthogonality integrals. Only one of them will contain the matrix element of the kinetic energy operator in single particle states. So, I have written this same expression on this slide because in the previous slide this expression was little crammed up in a small space. So, this is a magnification of the same expression so that you can look at these things terms better. This is the matrix element of the single particle kinetic energy operator in single particle states, which depend on the coordinates x k and you have got integration over k. Okay. This is integration over dxk, and of course, you have a summation over all k's going from 1 through n, and the rest of the integrals are all of these orthogonality integrals. The potential energy interaction is just the same. Okay. So, that term is not touched. So, you can exploit the orthogonality, carry out the sum, contract the Kronecker deltas over these terms, and once you exploit it, what are you left with? You are left with summation only over ek prime. Okay. That is the only term over which you need to carry out a summation. You do have to carry out a summation over all the coordinates x going from k going from 1 through n. You have got the coefficient c as before, but the coefficient c will have the argument t as before, but all of these single particle quantum numbers even prime up to en prime will all become the unprimed labels because of the Kronecker delta, except the label which goes into the matrix element for the kinetic energy operator. Okay. So, that is the only one which will remain. So, you are left with a summation over ek prime. There is no summation over other single particle quantum numbers, there is just one single summation over ek prime. Then there is a summation over k going from 1 through n. You have got the coefficient c, but the arguments are all unprimed except the kth one, which is ek prime. Then you have got this matrix element of the kinetic energy operator in the single particle states corresponding to the coordinate xk, and then the rest of them have given you the from the Kronecker delta a factor of unity which you have multiplied throughout. Again, the potential energy term is left untouched, that remains to be tackled with. Okay. So, this is what you get from the kinetic energy term. So, I have written it here at the top of the slide, and now instead of ek prime I use the letter w just to focus attention on that, because it is a particular state over which you must sum over, right. Ek prime is a dummy label, you can change it to anything you want, and just to remind us that this is the one which is being summed over, we write it as w. I am actually following the notation from Fetter and Wolleka's book, which I have referenced for this discussion. So, I am using the same notation as Fetter and Wolleka. So, I use w instead of ek prime. So, here instead of ek prime I have a w, other than that everything else is the same. So, all of these coefficients up to w, which are coefficients from E1 to ek minus 1, they remain the same, and all the coefficients, all the single particle quantum states after the kth one beginning with ek plus 1 up to En, they remain the same, and there is of course a time dependence. So, this is what we have got, and now we consider the two particle terms, the potential energy terms. We had deferred our discussion on the two particle terms, which we take up now. Now, the two particle part of the Hamiltonian is this half double sum over k and L and an interaction term V, which depends on the coordinates x and L, and this interaction we do not want to count twice. So, it is half of this double sum, okay, and you must exclude k equal to L. Okay. This is the two particle interaction. So, this has been written explicitly now as this, and you can write this half sum over k and L outside these summations signs. Okay. So, they are moved all the way to the left, and the rest of the terms you have got the summation over E1 prime up to En prime, which is written over here. You have got the coefficient c, which is here. So, this coefficient C has been written here along with the time dependence, and then you have got the 2 particle interaction terms which are being integrated out, okay, because you will have to carry out integration over all of these coordinates x1 up to xn. Now, this 2 particle interaction connects only the coordinates of xk and xl. So, whatever is neither xk nor xl is independent of this particular interaction, and those integrals can be factored out. They will give you essentially orthogonality integrals. Okay. So, we will exploit that now. So, only the terms which have got coordinates in xk and xl, they will be handled separately, and those are, so you have got a 2 center integral, integration over k and integration over L, dxk and dxl, and then you have got, this is an integral of a certain integrand. That integrand is the matrix element of the potential energy operator between psi E k dagger psi E L dagger, okay, with arguments xk and xl respectively, okay, and then on the right you have got ek prime and el prime respectively with arguments xk and xl, and the rest of the integrals over all the other coordinates will give you these Kronecker deltas, and then you can carry out the summation over E1 prime, E2 prime up to En prime and contract the summations, so that you are left with very few terms. So, let us exploit the orthogonality integrals. Okay. So, you are left with a 2 center integral, which is this, which is the matrix element of the interaction which depends on the kth and the lth coordinate xk and xl. This is an integral between the states psi ek prime psi el prime with coordinates xk and xl, and here you have got the adjoints psi ek and psi el with the coordinates xk and xl. So, this is the 2 center integral, integration being over xk and xl, and this double integral is then multiplied by a bunch of Kronecker deltas, and when you carry out the summation over all of these E1 prime and up to En prime, most of these will drop out because of the orthogonality. So, let us exploit that. The only thing that does not get dropped out are those with summations ek prime and El prime, which are the ones which are under the integration of this 2 center term, this potential energy term. So, you are left with a summation only over ek prime and El prime, whereas over here you had a summation over all the n quantum states. Now, you are left with a summation only over 2 of them, okay, but each is a set of 4 quantum numbers, mind you, okay, or 4, or it could even be more, because depending on the number of degrees of freedom the particle has and how many compatible measurements you can carry out, you will get those many number of single particle labels. So, it could be 4 or more. So, you have got this double summation, you have got the half of this double summation over k and L, k not equal to L, and then you have got this coefficient C as before. This coefficient C is coming from here, this is the 2 center term, this term over here is the kinetic energy term which we have already discussed earlier. So, we are now focusing our attention on the potential energy term, which has got this coefficient, time dependent coefficient, which contains the statistics, and then you have got this integral of the potential energy term. So, we have written this at the top of the next slide, which is this, and just as we label this summation over ek prime as W, we now focus attention on the summation over ek prime and El prime, and to underscore this point we label ek prime as W prime, ek prime as W and El prime as W prime. Okay. so that we know that the W's are the special ones over which the summation is left to be carried out, all the other summations have been carried out already. So, it is the same expression rewritten here, except for the fact that instead of E k prime we have used a W here, and instead of E l prime we have used a W prime here, and you have that the coefficient C as well, because the coefficient C had an E k here and an E l here. So, they get replaced respectively by W and W prime. Okay. Likewise, in the integral you have got the coefficients E k prime and E l prime here, and these get replaced by W and W prime over here. Okay. So, it is just the same expression which is rewritten with the W's instead of the E's. Now, plug in the statistics, and we have agreed that it is contained in the symmetry of the coefficient C. If the coefficient C are symmetric, you have bosons, and if the coefficient C are antisymmetric, you have the fermions. So, I will now discuss the case of electrons, because that is where most of the interest in atomic physics is, because you deal with a system of n electrons. So, I will first discuss the fermions, and for fermions, if you interchange these two labels E j and E I, then the coefficient C must change its sign. Okay. These are Fermi particles. Of course, if two of these labels happen to be the same, if E j is equal to E I, then this coefficient must vanish. Okay. This is nothing but a statement of the Pauli's exclusion principle, that for fermions, for electrons, you cannot have the same state occupied by two particles. So, what we do is we consider an ordered sequence of these single particle states. This is not necessarily in increasing order of energy. Okay. So, do not get carried away by the letter E. Okay. E is a set of 4 quantum numbers, remember. Okay. It includes the energy quantum number, but it could also have other quantum numbers. Okay. Some of these may be degenerate. For example, the 1s up and the 1s down in the helium atom, they have the same energy in the ground state. Okay. So, some of them may be degenerate. So, obviously, some of these energies will be actually equal to each other, but this inequality is an indication of the ordering and not a relationship between energies. So, do not get carried away by the letter E. It is not representing an energy, it represents a particular quantum states, and these quantum states you can always order in a certain way, in a predetermined order. You decide how you want to do it. Okay. You can put spin up before the spin down or vice versa, it does not matter, but you decide what that order is, and once that order is decided, do not touch it, do not tamper with it. Okay. And that ordering is what is indicated by this inequality sign. It is not that this is any energy or angular momentum less than that of the next, it only means that this set of quantum numbers will come before the next set of 4 quantum numbers, which will come before the next set, before the third set, and so on. So, there is a certain ordered sequence of single particle quantum numbers, and these coefficients are also having these arguments, the single particle quantum numbers E1 through En, and they are also arranged in the same order. So, all the information about the single particle states is now contained in a coefficient which tells us which single particle states are occupied and which are empty. Okay, this is where the importance of the occupation number formalism comes in, because some of the single particle states will be empty. Okay. You have considered infinite possibilities, but only n out of these infinite possibilities are occupied, because each single particle fermion state can be occupied by only one particle. There are n number of particles, so out of these only n are occupied, the rest of them are vacant. And now if you write occupation numbers n1, which is the number of fermions in state E1, the number n2, which is the number of fermions in state E2, and each of these numbers for fermions will be either 0 or 1. For bosons it could be anything, it could be 0, 1, 2, many, all. Okay? So you can have a number of different possibilities, and we will first focus our attention on fermions, and we find that the fact that which one is occupied and which one is not, this information is completely equivalent to the information which is there in the coefficient C. So there is a one-to-one mapping between the physical information which has gone into the coefficient C and the physical information which goes in this function f, which is a function of all of these infinite single particle quantum numbers, out of which only n will have a value 1 and the remaining will have a value 0, but which one will have will depend on which of these single particle states are occupied, all the others being vacant. So this is where all the information is contained. So this coefficient f, which is a function of these occupation numbers and time, is completely equivalent to the coefficient C, which is a function of these single particle occupied states and time. Now you have a many electron wave function, and this many electron wave function, which you can write as a product of these single particle states. So you plug in the statistics in it. So you have got a Slater determinant, which we have discussed in our earlier discussions, and also in the previous course at great length we dealt with the Slater determinant, especially in the context of the Hartree-Fock formalism. So your n particle fermion state is given by these elements of the Slater determinant. This is a normalized Slater determinant, as you can see, given the fact that we are dealing with single particle normalized states. So these elements of the Slater determinant are single particle normalized states of some one particle operators. So essentially what you are doing is you are superposing one Slater determinant over a second one, over a third one, over a fourth one. The coefficients contain information about which are the occupied states. The corresponding Slater determinant is used over here, and you have as many Slater determinants as are important to describe the correlations. The correlated many electron system will then be written as a superposition of very many Slater determinants, in principle infinite. Okay? But in most practical cases only one may be important, and in some others maybe 5 or 6 or 10 or 20 are important, or maybe a few hundred or even a few thousand. Okay? So the Slater determinant is made up of these elements which are time independent single particle states. All the time dependence is in the coefficient C and hence in the coefficient f. Okay? So the Slater determinant itself is independent of time, the time dependence is in the coefficient f. Sorry?
E1 0. Yeah.
This is the particular Slater determinant that I considered, okay, which is the 0th one, but then you may have another one. Okay, so just to indicate that this is a particular Slater determinant, I have used the superscript 0. So now we go over to a fermion occupation number vector. So, the n particle system can now be described by a vector in something like a Hilbert space, but this space is what we shall call as an occupation number vector space. So, these are vectors very similar in properties. You can define their norms, you can define their orthogonality relations, you can define their completeness, very similar to how you dealt with single particle vectors in a Hilbert space. And we now introduce the fermion occupation number state vector, which has this information. These occupation number for single particles can be either 0 or 1, and for each n1 both the possibilities are there. So, you should sum over n1 going from 0 to 1. Okay. And the fundamental properties of the fermion particles is contained in what are known as creation and destruction operators. So, A is the destruction operator, A dagger is the creation operator, and the statistics is completely defined by these operators. These are what are known as fundamental anti-commutation rules. The statement of these anti-commutation because this is A comma A dagger, which is A dagger plus A dagger A. So, A comma B with a plus subscript after this rectangular bracket is the anti-commutator AB plus BA, and this anti-commutator you have got for A at A dagger equal to delta RS, this is the Kronecker delta. So, it is equal to 1 when R is equal to S, otherwise it is 0, and for 2 creation operators the anti-commutator is 0, and also for 2 destruction operators the anti-commutator is 0. Okay. So, now you have the boson occupation number state vectors, which are also defined in a very similar way, except for the fact that the creation and destruction operators have got different properties. But now there is no such constraint that these numbers n1, n2 etc. are either 0 or 1, they can be anything, they can be 0, 1, 2, 3, 10, 100, many, right. But the summation over all of these occupation numbers must add up to the total number of bosons that you are talking about. Okay. So, that is the only constraint, and these occupation number vector states will be operated upon by creation and destruction operators, which have a different set of rules, and these are given by the boson creation and destruction and commutation rules. AB with a minus is AB minus BA. This is the usual commutator that we work with, especially when we deal with the position momentum operators. Okay, it is the same commutator, but in the case of the Fermi operators you have the anti-commutator. So, where is the statistics? It is contained in the wave function in the first quantized formalism. The wave function is either symmetric or antisymmetric under the interchange of 2 particles. Then we found that the statistics was contained in the coefficients C, okay, and the information in C is the same as the information in F, which is in the occupation numbers. So, how do the creation and destruction operators operate in succession? Okay, that is where the statistics is contained. So, all the statistical information is now contained in these creation and destruction operators, which is why they are different for Fermi particles as for the Bose particles. So, you have got the Fermi particles here that we are working with. Let us ask this question: what would happen if 2 creation operators for the Fermi particle in S state operate in succession one after the other, what would happen? You expect it to go to 0, but that is from your knowledge of Fermi-Dirac statistics from first quantization. You should arrive at the same conclusion on the basis of the anti-commutation rules for the Fermi operators, okay, because this is what we have defined, which we have now introduced, and these are the focal points of interest in the context of the statistics, that all the statistics is contained in the anti-commutation properties of the creation and destruction operators. So, using the anti-commutation properties alone, you should arrive at the same conclusion, okay, without referring to anything else. So, if you did that, the two operators, the two creation operators for the quantum state S operating in succession of each other, a succession one after the other. So, it is half of twice of this, right, twice of this is the sum of these, and the sum of these is just the operator AS dagger anti-commutated with the same. And what is that? That goes to 0, right, and that goes to 0 not from your previous knowledge of the Pauli exclusion principle, but from the property of the anti-commutation property of the creation operators. So, all the information, the statistical information is now contained in the anti-commutation relation. So, using this property you find that these two operators when operated in succession give you 0, which means that you cannot create a fermion in a Fermi state which is already occupied. This is the Pauli exclusion principle. So, likewise you can understand other properties of the number operator. So, these are the fundamental anti-commutation rules, and if you now have the same state AS and AS dagger, then this for R equal to S will be equal to 1. So, now if you write the operator AS dagger AS, what do you get from this expression? From this expression you get that AS dagger AS, which is the number operator, is 1 minus AS dagger, okay. Now, this being the fact, if you now take the square of this, okay, if you take the square of this, you have got 1 minus AS dagger followed by 1 minus AS dagger. Now, you expand all of these, so you get 4 terms, 1 minus AS dagger, then you get another AS dagger from this, and then you get these two minus signs give you a plus sign, and then you get AS dagger, again AS dagger, that is what you get, right. So, you have got 4 terms over here. Now, out of these 4 terms you can anti-commute these two, because AS dagger, if you want to move AS behind AS dagger, you will get 1 minus AS dagger, right. So, I have exploited the anti-commutation between AS and AS dagger, and using that anti-commutation I get these two terms 1 minus AS dagger. From this you get AS multiplied 1 multiplying AS dagger with a plus sign. So, you get AS dagger plus, which cancels one of these, and you are left with only this, which is 1 minus AS dagger, right. From the residual term you have got AS dagger, which we saw in the previous discussion already goes to 0. So, you get only 1 minus AS dagger, which is nothing but the operator NS itself. What does it tell you? That the square of NS is the same as NS, right. And if that is the case, then this being an operator identity, the only two possible eigenvalues the occupation number operator can have are either 0 or 1, okay. Now, this we already knew because of our familiarity with the Pauli's exclusion principle, but we are now able to actually deduce it from the anti-commutation properties, which has got all the statistics built into it including the consequences of statistics such as the Pauli exclusion principle. Okay. So, this is the power of the anti-commutation rules for fermions, and you have got the same power for the boson commutation properties. So, you have got these properties, the square of the occupation number is the same as Ns, and you find that the creation operator, if it tries to create a particle in a state which is already occupied, then you get 0, because you cannot create a particle in which you already have occupancy, nor can you destroy a particle from a vacant state, from a vacuum state. मरे हुए को क्या मारना, right? If there is no state in it already, you cannot destroy a particle out of it. So, A, the destruction operator operating on the vacuum state, will give you the number 0. So, keep track of the difference between the number 0 and the vacuum state. The vacuum state is a vector in the occupation number state, the number 0 is the arithmetic 0 which ancient Hindu mathematicians invented. Okay, so, these are two different things. So, these are your fundamental properties, and they explain to you why this should be called as a destruction operator, why it should be called as an annihilation operator, why its adjoint should be called as a creation operator, and why this operator A dagger A should be called as the number operator. So, all of these operators acquire a particular significance in the context of the properties they attain from the anti-commutation properties of these operators. Now, that is where the physics is, that is where the statistics is, okay? And they tell you which single particle states are occupied and which are not occupied. All properties like Pauli exclusion and principle etc. are contained in the properties of these creation and destruction operators, and this is a good point to take a break here and continue from this point in our next class. And on the lighter vein, I will like to quote Sakurai from his book Advanced Quantum Mechanics. Sakurai has got two excellent books, one is Modern Quantum Mechanics, which you have used, the other is Advanced Quantum Mechanics, which also some of you would have used, which I strongly recommend, which is very good. And in this book Sakurai has got a rather interesting quote. He says that we might say that the three operators A dagger A and A dagger A correspond respectively to the creator, the destroyer, the Brahma, the Shiva, and the preserver, Vishnu. Okay. So, these are the creation, destruction and number operators. This is where the physics is sitting, okay? That is what our interest is, okay? All the physics is sitting over here in the properties of these creation and destruction operators, and we will continue from here in the next class and see how this formalism helps us deal with correlations. That is our fundamental interest, okay? In the absence of correlations, we already know how to deal with the n particle electron system, that is the Hartree-Fock theory, but they do not include any Coulomb correlations. When you want to include the Coulomb correlations, when you want to go beyond the Hartree-Fock, then you must have a many body correlation formalism, which is why you have a superposition of all of these Slater determinants. And because it is so messy to work with these factorial n terms in the Slater determinants, it is now going to be very convenient to deal with these numbers, because now you just have to deal with two numbers, either 0 or 1, it is all binary, okay. So, it is the whole physics, the same physics, but we are going to have an operational convenience. So, it is not like a fundamental step in quantization as we take from classical mechanics to quantum mechanics. That is a big step. That step involves dispensing with causality and determinism of classical mechanics and replacing it with the uncertainty principle and measurement and the idea of compatible measurements and so on, okay. That is a very big jump, whereas in this case it is just a formalism which you are moving over from the first quantization formalism to a second quantization formalism, which is going to make it very easy. So, it is convenience, mathematical convenience, mathematical elegance, and not like a fundamental step involved in quantization. So, it is called a second quantization because now you have got the wave functions which get quantized. I will deal with that a little later, but actually the creation and destruction operators become quite significant in the context of relativistic formalism, because in relativity you have matter and energy which you can convert from each other. So, you can actually create particles when no particles existed, okay, or you can annihilate an electron against a positron and create energy, right. So, you can actually destroy or create particles in this relativistic formalism, and then second quantization becomes really necessary to describe those processes. But in the absence of those terms, and that is not the domain of interest in atomic physics, because our interest in atomic physics is at low energies, okay. Now, these processes do not take place at low energies, you have to go at least above the rest mass energy of 2 electrons, okay. So, which is above a million electron volts. So, that is not the domain of atomic physics, the structure and spectroscopy that we work with in atomic physics, but for us it is mathematical elegance, it is mathematical convenience, and a great convenience at that. Any question?
We can call it the number operator only because of the first two, I mean when the Heidegger
Because its square is equal to itself, that is an operator identity which tells you that its eigenvalues can be only 0 or 1, okay. The eigenvalue of the number operator is either 0 or 1, and that is the number which tells you whether a single particle state is occupied or not. And in the case of fermions, either it is occupied or it is not occupied, there is nothing in between. So, that is what justifies its name as the number operator, because its eigenvalues can be either 0 or 1. In the case of bosons, it actually gives you the number of bosons in that particular state. Ket 0 is an occupation number vector. You can do algebra in occupation number space. You can construct a linear superposition of 2 occupation number vectors, just the way you can do a superposition of 2 Hilbert space vectors, right, and you can add a null vector to another vector which gives you the same vector, but it is a vector in the Hilbert space, whereas the number 0 is not a vector in the Hilbert space, it is the arithmetic 0.
My question is,
yeah,
suppose when we have an electron in particular state and we are trying to create an electron in that space, we are not getting a vacuum state, we are getting a 0. What I mean, that's not, we are not getting a 0 state, right? It's just a 0.
you do not get a vacuum state.
Yeah, that's what
You do not get a vacuum state by trying to destroy a particle in a vacuum state. What this equation is telling you is that you cannot do that. It is not that you get vacuum by destroying a particle in the vacuum state, because there is no particle in the vacuum state. So, you just simply cannot do it, that is the number 0. So, on this note we will stop here for now, and then we will continue the discussion from the next class.